Howdy. In this video, we're going to take a look at some ideas about chemical kinetics, which I tend to think of this one as being pretty much a review of some things from general chemistry. I'm aware that a number of you are currently in a kinetics class taught in your own department. I believe that some of you have probably already taken that class, but at least as far as I know, there's also a subset who have not. And so if you're in one of those first two groups, then what's in here might seem familiar to you. On the other hand, if you haven't thought about kinetics since Gen Chem some number of years ago, then the refresher is probably a good idea. Starting out with just putting together the idea of a rate law and how we measure rates. So on the top of the slide here, we have what is intended as just a generic chemical reaction. So in that equation, the uppercase letters represent the substances, whatever might be the reactants and the products. The lowercase letters represent stoichiometric coefficients that balance the equation, okay? I wrote two reactants and two products. There's nothing special about that. There could be arbitrary numbers on either side. It would still work the same. When we talk about rates of reaction, the first thing to remember is we define that as a change in concentration over a change in time. And then we put together what is known as a rate law, okay? First, to define the rate, we want to be able to define the rate in terms of the change in concentration of any one of the substances involved, because the rates of change of the different substances are all related by the stoichiometric coefficients, okay? So if, for example, my reaction used 1 mole of A and 2 moles of B, then the concentration of B would change twice as fast as the concentration of A. If A and B are reactants, then as time goes along, if we start with just A and B present, the concentrations of A and B are going down, while at the same time the concentrations of C and D are going up. So this equation here takes into account all those ideas. It says the rate is defined in terms of the concentration of any one of our four substances. If we were actually trying to measure the rate, we would probably just choose based on experimental convenience which concentration we wanted to measure. If there was something about one of them that made it easy to detect, we'd probably pick that one. You'll notice in front of the reactants here, I've got minus signs. Those are meant to make sure that the rate itself is defined as a positive quantity. Okay, so dAdt, for example, is going to be negative because the concentration of A is going down. So that minus sign makes sure that the rate definition is positive. Okay. If you look to the right-hand side for C and D, you'll notice there are not minus signs in front of those, and that's because those concentrations are going up. So dC dt or dd dt, those are positive already. Then the last thing included here is to divide everything by its stoichiometric coefficients. What that does is it makes sure that all four of those definitions of the rate should give us the same outcome. All right, because again, if one substance has a larger stoichiometric coefficient, then its concentration is going to change more sharply than one that has a smaller coefficient. In principle, it's possible for the rate to be a function of any or all of the concentrations, right? So this says it could be all of them. If I have A, B, C, and D in there, I could have a rate law that had all four substances in it. That would frankly be kind of unusual. Typically, in particular, the products are relatively unlikely to appear in rate laws, although they do sometimes. The reactants, often just one or two of them might appear in a reaction that's more complicated, okay? And that's because of things like rate limiting step arguments and the like that lead to those outcomes. If the products are present, that gives interesting kinetic outcomes, right? If the products are in the rate law, in many cases, the accumulation of product might slow down the rate of reaction, in which case, if you were trying to do that reaction for some practical purpose, you'd want to find a way to be separating out the products over the course of the reaction so that they weren't accumulating and slowing down your reaction. Perhaps the most interesting case is there are a small number of reactions for which the presence of products actually speeds the reaction up. That's known as autocatalysis, and reactions that have that feature often tend to result in explosions because it means essentially that the faster it reacts, the faster it accelerates, and that leads to everything reacting in a very small window of time, which is sort of a definition of something that's likely to explode. So rate laws turn out to be written generally of the form down here, okay? So this one happens to have all four substances in it. Again, that would be an unusual outcome. The rate is given by a rate constant K in front of things. Important to keep in mind, that is not Boltzmann's constant, right? So in the slides in this segment of the course, I'm gonna try very hard to make sure I put the subscript B on any that are Boltzmann's constant, because that one will still be sticking around with us some more. Whereas without that, it's a rate constant. Okay, so if you're taking notes manually, make sure that you get on top of those, or you can get yourself really confused later if you have equations that have like K equals some function of K. It's going to look really strange. These are concentrations raised to powers, where here I've used the Greek letters alpha, beta, gamma, and delta for the powers, and those exponents up there are known as the order of reaction. They are typically, but not always, small whole numbers. The vast majority of them are either 0, 1, or 2. Occasionally one sees small rational fractions up there, okay, but that's much less common than the 0, 1, or 2 case. If they're 0, that effectively means that that particular substance does not influence the rate. When I say not all the substances are usually present, another way to say that is they're 0 order, which means they just don't matter to the rate. If it's the substance in the reaction, it still has to be there, but the concentration of it would become unimportant then. In general, there is no requirement that those exponents or orders of reaction match the coefficients from the equation, okay? Which is why I use the Greek letters down there for the orders of reaction and the lowercase letters up above for the coefficients to balance the equation, okay? Sometimes they will match because, again, most of those exponents are going to be 1s and 2s, and a lot of chemical reactions have coefficients in them that are 1s and 2s, so it can often be that we will have a coincidental match, and then there are a special category of reactions referred to as elementary reactions or elementary steps, in which there is an actual explanation for why they tend to match, but that's another topic. The rest of this video is going to talk about integrated rate laws, okay? So the rate law itself, typically we have to find that by experiment. And so when we teach Gen Chem, the first way we usually present for finding a rate law is what's known as the method of initial rates, which says you measure out your reactants, you mix them together, and you try to measure the rate of reaction right at the beginning. Okay, then you do the experiment again using a different concentration of reactants, and you see what happens to the rate. From that, you can piece out what those exponents are. Especially what makes that simple is the fact that, again, the exponents are usually small whole numbers. So you're basically, if you double the concentration, you're trying to see, did the rate stay the same? Did it double or did it quadruple? And those are pretty easy to tell apart, right? When we do that experiment, the various trials have to be at the same temperature, because that rate constant, I think I didn't mention this on the previous slide, but it's constant only for a particular reaction at a particular temperature, right? It is not a universal constant like Avogadro's number or Boltzmann's constant. It's a constant in some very narrowly defined circumstances. The integrated rate law is another way to find a rate law, actually, is to make some plots that are based on the integrated rate law. It's also a way to sort of map out the trajectory or the pathway of a reaction over time. The argument goes a lot like doing classical physics, is how I always explain this to my freshman class, because they're taking that course often at the same time. We know the initial concentration of the reactants, and if we know the rate law, then that's a lot like doing a physics problem where you know the original position and velocity of a part of an object, a projectile, say, and then you can figure out its trajectory. Where's it going to be at different times, right? In this case, for our reaction, the where's it going to be corresponds to what are the concentrations going to be. So if I think about the trajectory of my reaction, it's just saying this is how much of everything should be there at different times, right? So mathematically, this means I have a relatively simple differential equation, and I have I know the initial conditions, and I figure things out from there. The good part is that you're not afraid of simple differential equations, so I get to actually do the mathiness here, which is pretty simple. From your point of view, we kind of have to like sort of dance around this some in the freshman classes, because a lot of people in there are not familiar with integrals at the time that we might be talking about them. So I like doing this part this way. We have our reaction. I'm skipping over the 0 order case because that's kind of boring. That just says the rate is constant. And so there's really not a lot to do there. If I have first order reaction, my reactant just turns into products. The products might very well be more than one molecule, but that's not important for what I'm doing right now. My rate law just says that minus dA dt, the minus sign again because A is going down, is just equal to K times A. It's first order, so we could say it's K times A to the first power, but there's no reason to write that there, right? Rearrange that to separate the variables, and I get dA over A equals minus K dt. Right, so that's got my A on one side, my T variable, or my dA on one side, my dt on the other. Now we need to integrate that because that's how we're going to get the integrated rate law. Bounds of my integral, I'm going to go from time equals 0, the beginning of my reaction, to some later time, which I'm going to call t. That irritates mathematicians when we do this. We're using the same symbol to represent the variable and one of its values. And so that's a little sloppy, but that's what we do in chemistry books, so I'm going to stick with it. My concentration integral, meanwhile, goes from just A0, the concentration at time 0, to A, which is the concentration at whatever the later time t is that we're looking at, okay? I have the integral on the left of dA over A, which we know gives us log of A, and on the right, I just have the integral of minus K dt, which just gives me minus KT, right? So that gives me this form over here is the one that would come out first from doing the integral. And if I recognize that, I can say that's an exponential decay, right? So I can say that means the concentration starts at A0, the initial concentration, and then it decays exponentially with the steepness of that exponential depending on the value of the rate constant K. The bigger K is, the more sharply it's going to go down, all right? Let's take those equations and see what a couple of plots would look like, okay? So the first one I'll do is I'm going to sketch these in here, and I'll do my best. I'm not the greatest curve sketcher. But the first one is concentration versus time, and we said that's an exponential decay. So let me just draw some decent approximation to an exponential decay there. It will go down something like that, okay? The second one is going to be a linearized graph, which first I will draw in the graph, which says natural log of A versus time. And if I plot that one, I should get a line that's going downward. It turns out that the lower equation on this slide is the equation for that line, right? Because this thing, log of A, is the y-axis, t is my x-axis, which means that minus k there is my slope, and this part is my intercept. For that, right? So that just reminds me that the slope of this graph is equal to minus k. So this is actually an alternative way to find a rate law. If I took some data and plotted, say, the log of concentration versus time, I could look at the graph and decide, is it a line? If it's a line, then my reaction is first order. And if it's a line, then the slope of that line tells me the rate constant, right? The rate constant is always positive. So when the graph is going down like it is here, the rate constant is going to end up being minus k, which is also what the equations tell us. When I first learned to do this, we used to always emphasize making the linear graph because humans are actually quite good at looking at a graph and deciding do those points look like they're on a line. Humans are less good, most of us, at looking at a curve and deciding if it's an exponential or not. Nowadays, if you were actually trying to do this, you presumably would be fitting your graphs in some sort of software package, and your software frankly doesn't care whether it's fitting an exponential or fitting a line. So you could also just look at a fit to this graph and see, is it an exponential? And if it is, then you can still extract the rate constant from that because this one is just that A is A0 times e to the minus kt, right? And so the exponential would tell you what the fit would tell you what that k value was, and you could do that just as well. Second order case, if there's just one reactant, is still simple. The two reactant case is actually a lot less simple, and I did sneak in a little bit of that to finish this, this video out, although that one is definitely beyond the scope of normal Gen Chem, I will confess. So my reaction, my rate law now says dA dt is second order, so it's just K times concentration squared. Again, the second order refers to that 2 being up there. Separate my variables again, and I get dA over A squared equal to minus K dt again. Do the same integral, A0 to A and T equals 0 to T. When I do that, I have the integral of dA over A squared, which should give me minus 1 over concentration of A, right? So if I take that and set that up, my first outcome is over here. That's a bit gawky looking because it's got minus signs literally all over the place. Take that and rearrange it a little bit, and we would get this form on the right, which says that I have an equation which is going to be a linear equation in terms of 1 over a. So that'll point to a way to plot this thing to make a line. So those are my equations. The first plot, if I take concentration of A versus T, it's going to go down. It's going to look sort of like this. Now, that one should not be an exponential. It should actually drop off a little bit more sharply than an exponential. I have a graph that has a pair of functions plotted on it momentarily that I can talk about that a little bit more detail. If I take this graph, A is going down because it's the reactant concentration. So 1 over A is going up. And again, this equation is the equation for that line because that's why this piece T is X. So that's my MX plus B, right? All of which points to the fact that the slope of this graph is just equal to K. So in that instance, I could take the data, measure the concentration as a function of time, plot 1 over concentration versus time, check and see if it's a line. If it's a line, then the slope of that line will just tell me the rate constant directly, okay? You can get units for the rate constants out of this thing too. The units for rate constants are frustrating because they change with the order of reaction, right? So in this case, it's relatively simple to say it's going to have the units that come from the slope of that graph, right? So that means it's going to have, from the y part, it's going to have 1 over concentration, let's say 1 over molarity. And then from the x part, it's going to have time, let's say seconds. So that means this thing would be 1 over both molarity and seconds, okay? I'm going to flip back for a second. In this one, the units for a first order rate constant should just be 1 over time, say 1 over seconds, if seconds are my time unit. To see that from the graph, we have to do something a little funny. Before we take the logarithm of that concentration, we have to make it into a sort of standardized or normalized concentration. Effectively, we have to divide off the units because you can't take the logarithm of molarity. That doesn't actually correspond to anything physically. And so there's a little bit of a trick there. You can also always find the correct units by just solving the rate law and dragging units for molarities and times through it, and that will work out as well. A couple words about half-life, because it's an interesting way of talking about kinetics that is used a lot in a couple of fields. The half-life, generally just written as T1 half like that, is the time it takes to use up half of the initial amount of reactant. If a reaction is first order, knowing the half-life turns out to be the same information content as knowing the rate constant. I mentioned there's 2 fields where half-lives are used quite commonly. One is radioactive decay, which is always a first order process. And the other is a rather different line of work. It generally has to do with the pharmaceutical business because the lifetime of a medication in your body is generally a first order process. And so some things about half-life are involved in figuring out the time between doses and the required dosage and what have you for a lot of medications. If I wanted to get to the result for this, I can take my first order equation. So this is the linear form of the first order integrated rate law, okay? Take that and rearrange it to solve for t, and we get this form here, okay? To figure out what's going on at the time we're at the half-life, all I do is put in the fact that when I'm at T1 half for t, then the concentration of A is half of what it started with. Okay, that means that A0 over A is now equal to 2 because half of it is still there. Put those things in and I get the result down here, right? Which says that the half-life is just natural log of 2 over the rate constant. So that tells me that if I know either one of those things, either the half-life or the rate constant, I can know the other one, right? They're literally the same amount of knowledge. They have the same information value is a way of saying that in that case, right? And so people that do work with radioactive isotopes almost always talk about half-lives as a way of describing like how long-lived something will be, and rarely talk about things in terms of rate constants. That half-life idea becomes kind of worthless, frankly, for things that are not first-order reactions. So this is the second-order case here, and if I figure out the half-life for a second-order reaction, you can walk through the math, but the important message is that half-life is a function of the initial amount. that means that knowing the half-life is going to always depend on what amount did you start with. So it's not really a useful thing. A table of half-lives for second-order reactions would have to include the initial concentrations, and that makes it kind of a more or less worthless idea. Okay, so in this instance, the knowledge content of the half-life and the rate constant are not really the same, right? If I know I've got three things in that equation: the half-life, the rate constant, and the initial concentration. So now I have to know two of them to get to the third one, right? They're no longer the same bit of knowledge. This is a graph I promised a moment ago that says it's just got a couple of data sets on here that are totally just made in Excel. The red ones are a first order reaction. The blue ones are a second order reaction. They both start at a concentration of 1 just for simplicity. And they both have rate constants that are numerically equal to 0.693, which happens to be the natural log of 2. I picked that number very specifically because it means that the half-life for my first order reaction is 1. So 1 second is my first order half-life here. Starting from 1, if I come down here, you can see that after 1 second, I'm at 0.5. After 2 seconds, I'm at 0.25, and so on, right? So I have a constant half-life, and I could keep ticking those off as I went across, so the half-life is a worthwhile quantity. If I want to look at the second order case, when I get down to 0.5, so here, my second order half-life for the first time is somewhere there, between 1.5 and 2 seconds, let's say, based on my scribbles. If I come down to the 0.25 point and just try and dash out to the curve, you can see it takes a lot longer to get down there, right? So my half-life is growing as time goes along, and that means, again, it's not a fixed value, right? If you look at these, my blue curve, the second order case, the curve is going down more slowly than the first order case. That's because after a little bit of time has gone by, the concentration has shrunk, right? Shrinking the concentration slows down the second order reaction by more than the first order reaction because the second order rate law has concentration squared in it, which of course goes down more rapidly than concentration does. Lastly, I'll just point out here, this thing runs out to about 10 half-lives. 10 half-lives is often taken as a rule of thumb for when you can say that the stuff is essentially all gone. So if you were responsible for storing radioactive waste or something, you might say, I have to keep this stuff secured until at least 10 half-lives have passed, because at that point, you're down to just, 1/2 to the 10th power of your initial amount of material, which means that you don't have a whole lot left at that point, almost independent of what you started with, okay? I did include in here, just for a little bit of entertainment, one somewhat more complicated thing, okay, which is we always do the second order rate law for the single reactant part, and that's part of almost every Gen Chem textbook that exists, and I know that from having written one. The more complicated case is if there are two reactants, within that scope, if it's first order in each of those, that will give me a second order reaction overall, right? If you do this one, the math is a little bit gruesome. So in the slides that I posted, I included some grisly details for anybody that's a glutton for that sort of thing and just wants to look through it. But essentially the argument would go like this. I start off, this is my rate law, right? So it's first order in A, first order in B, for second order overall. I start off with known initial concentrations, just label them with a 0 for time 0, okay? I introduce an X here, which is just essentially how much of the things have been used up, right? And we're also implying here that A and B have identical coefficients in the reaction for this purpose, so that the amounts of decrease of concentration of A and concentration of B are the same. That lets me set up my rate law essentially in terms of this X quantity, okay? So that lets me say that I can make this equation here that will tell me how the rate of the reaction is going to depend on the progress of things, okay? If I take that And I'm skipping a lot of steps here, I'll be honest, but I did include them. So like I said, you can look at them if you'd like. Take that equation and we're going to integrate it again from t equals 0, x equals 0, up to t equals t, and concentration just goes to concentration of A and concentration of B that are unlabeled. After a lot of math and a lot of substituting of various things, you can get to this result here, okay? That's a pretty still intimidating looking thing, but it is linear, right? So that says if I made a plot of the right-hand side of that graph versus time, I could use that as a way to find the rate constant for my, my second order reaction, okay? There are models like this and equations for the integrated rate laws for all sorts of strange combinations of reaction kinetics, most of them beyond those simple zero order, first order and second order one reactant. The rest of them tend to be at least this messy looking, okay? And so they are sometimes used, but they're not really the stuff of textbooks. I just kind of wanted to pop out here the fact that it is possible to derive equations like this for more complicated kinetics. It just requires a lot more willingness to struggle through math and persevere and get things straightened out at the end. All right, except for that one little bit at the end, that's like I mentioned at the beginning, as mostly things that in general ways are talked about in my Chem 107 class, but a bit of a brush off and refresher for anybody that hasn't been doing kinetics for a while. Thanks.